are starting on the memory hierarchy, something I'm pretty familiar with. Discussed last night that I was going to speed read through this entire chapter. It is, I think, about 70 was something pages. So yeah, I'm going to speed read through that. I'm going to start marking these things as whether I showed up for them or not. So if I do Command Control E, I think it is, check mark. Yeah, look at that. Save. See, that's what I don't like. If I save this, update recurring event, then it updates it. Oh no, it doesn't update it because it's changed. Okay, good. It's a bit of a weird UI there. Just this event, yep. And then I'm gonna do the same thing for here. And I definitely did it here as well. Did all four. So what do these check marks mean? They are an indicator that I showed up and I did some amount of work. I've agreed to commit to wherever I have a stream on my calendar. I'm going to show up and I'm going to do at least 5 minutes of work. And if I feel like shit and my brain doesn't want to learn and it's in complete rebellion, then after 5 minutes I can either change and do something completely different. I can read a different book, or I can read a super casual book like The Soul of a New Machine like I was doing on Sunday night. Or I could just piss off and do whatever I want and just end the stream. But I have to show up and I have to commit to doing at least 5 minutes of effort. Because the problem that I get into is that, like I'm starting a little bit early today because I woke up early and I got to the gym early and I got my shower and breakfast in, and so I got onto the stream early. But some days, you know, my gym session runs late. I'm stuck in traffic driving home, and I'm just not able to get onto stream on time. And the problem with that is that if I'm 15, 30 minutes, an hour late to a scheduled study stream, then sometimes I just don't do it. And that's the problem right there. Is if I don't do it, if I don't even show up and try to put forth the most minimal amount of effort, even if it's just 5 minutes, then I just waste that entire block of time. And that gets in my head and feeds into the next block. So then I'll try to escape the negative feelings from that by like going on YouTube or whatever. And it creates this vicious cycle of escaping from the anxiety and the part of my mind that's telling me that I fucked up. Escaping from all that anxiety, and in escaping from that, I end up skipping the next stream, which then is my next opportunity to study. I then escape from that, and it kind of just amplifies to the point of like, I'm not getting anything done. I'm wasting days upon days of my life just like doing garbage. And I end up staying up late because I'm on this addiction machine, this internet addiction machine that we've created. And I'm not able to get to bed on time, which means that in the morning I get into the gym late, and it just kind of, now we're just falling down the hill. We're tumbling down the hill. And so to prevent that entire thing, there's this concept that I ran into in Atomic Habits from runners. And the idea is that if you're committed to training for running, set the bar incredibly low for your training sessions. And say like, all I have to do is put my shoes on in the morning. I don't have to run. I just have to get up, put my shoes on, and if I don't want to run, I can take my shoes off and not run. But you commit to doing that bare minimum, and inevitably what happens is your brain has already put the shoes on. It's like, it would be stupid if we don't run. So you go out and run. Same thing with these streams. I'm committing to getting on stream to study and getting at least 5 minutes of work done. That's my commitment. And so I'll put a check mark on every stream, every green box here. I'm going to put a check mark whenever I do that. And whenever I don't do that, I'm going to put a red X. And then I'm going to report that to my accountability pod so that they are aware of how I'm doing. So I can hold myself accountable and have them hold me accountable. Oops. Okay. Just did my report. All right, I'm in that mood right now where I'm I thought I was going to just jump right in and start reading, but I'm not feeling it. So it might be one of those, put my sad light on, or happy light on here. I'm gonna get my matcha in me. I was thinking about not drinking any caffeine this morning, but I decided against it. Friday's my day off. 0 caffeine, outdoors. Bring my caffeine levels down. But yeah, I want to get shit done today. This is so stupid, this happy light. It just dies on me constantly. hate this thing. The buttons are all jank. It decides to die randomly. It's the second time I've... Yeah, see, it just died on me again. Yeah, doesn't have enough juice, I guess. I mean, it's sitting there plugged in, charging. So stupid. Alright, let's do something to warm my brain up here so that I actually want to read. Okay. I mean, this stuff isn't hard. The Memory Mountain. Wow, I accidentally skipped ahead a lot. Maybe I do some brilliance, just to get my brain doing something. Okay, what am I doing here? Brilliance. I'll do it over here. Brilliance. Counting operations, testing the amount of time it takes for an algorithm to run requires an implementation in a specific programming language on a specific computer. It's a lot of specifics. We often want to assess speed in a way that's more inherent to the algorithm itself. Used by counting the number of basic operations that an algorithm has to perform. For algorithms that manipulate numbers, we could count the number of algorithmic operations. For algorithms that manipulate arrays, we can count the number of times array locations are written to or read from, the number of times elements are compared, or the number of times elements are swapped. Here's an algorithm for finding the smallest element of an array. It's a linear time of n. It works by going through the array from left to right, keeping track of the smallest element when it is encountered. Yeah. I hate their pseudocode stuff. How many times does this algorithm access an array of element? An element of the array, n times. How many times does the algorithm compare a value from the array with a different value from the array? N minus 1. Thus, we could describe the cost of this algorithm as n array accesses or as n minus 1 comparisons. Now let's consider selection sort. In this example, it sorts an array of size 4 containing elements 4, 2, 7, and 3, originally in that order. I'm so tired. So selection sort is where we go in, we search the array, we select the element, then we move it into the position, or do a swap, basically. So that'd be all n squared, because we got 2 for loops. So we go from the current to the, from 0, for current from 0 to length of a minus 2. Because by the time we get to a minus 1, it's already sorted. You can skip over that element. We don't have to swap it with itself. So we set the min index to current, and then for I, from current plus 1 to length of a minus 1. If a sub I is less than a min index, then we set min index I, otherwise we swap a current and a min. Yeah. Yep. I don't need to walk through this. How many comparisons between 2 array elements were used to sort the array? I didn't actually count the comparisons, but since there's 4 elements, there'll be 1 comparison, 2 comparisons, Can I go back? Yeah, I can go back. Let's see. Boom, 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 boom. One comparison. Didn't need a swap. Two comparisons. Three comparisons. So we got three comparisons the first time, two comparisons the second time, one. So 3 plus 2 plus 1. So it'd be 6. Yeah, 3, 2, 1, 6. How many swap instructions were used to sort the array? Well, if we go back to the original, so 4 and 2 are out of order. So 4 and 2 need to be swapped. Right? Yeah. So that's one swap. That 7, 4 and 3 need to be swapped. And 7 and 4 need to be swapped. So it's 3 swaps. Here's selection sort for a large array containing 4, 9, 3, 2, and 7. It used 10 comparisons to sort this array. Yeah, it's 4 plus 3. It doesn't use 10 comparisons. It uses much more than that. Well, I guess it'd be 4, then 3, which would be 7. Then 2, then 1. Oh, yeah, it'd be 10. Yeah. I just counted wrong. How many times is swap instruction executed? Let's see. So it's going to be none on that. No, there's 2 here. So one swap on that. Swap it. Another swap on this with 4. Do 2. Swap it. And then another swap of 7. 3. Oh no, that wasn't a, is it a swap? Sorry, I wasn't counting. Swap there, 1. Swap with 4s, 2. Five is already placed, no swap needed. Yep. And then 9 and 7. So it'd be 3 swaps. What the fuck? Did I not count right? Alright, let's count again. I hate this. 4, I can swap with 2. So it's going to be 1 swap. 1 swap. Swapped. 9 swap with 4 is going to be 2 swaps. 5 swap with 7. The 5 is in place, so no swap. 9 swap with 7. It's 3 motherfucking swaps. It swaps index to. That's not a swap. I guess the algorithm is implemented in a way that it's a swap, but you would never swap an index with itself. It's like doing work that you don't need to do. Yeah, it would be helpful. The outer loop runs for n minus 1 times and does n minus 1 comparisons the first time through, n minus 2 the second time, and so on down to the comparison the last time. So it's basically creating a triangle, so that's why it's divided by 2. We'll skip the algebra, but adding these up gives n squared minus n divided by 2 comparisons in all. I really wish you wouldn't skip the math. That's where insight is. I mean, just graphically, if you have n minus 1, and they have n minus 2, n minus 3, n minus 4, n minus 5, all the way down to n minus, in parentheses, n minus 1, just going all the way down to 1. So you have this kind of like triangle area. But then that top row, because you did n minus 1 the first time, you also have a whole row that's gone. So if you conceptually think of it as n squared minus that top row, which is the minus n, divided by 2 because it's a triangle. Just graphically, intuitively, that makes sense without doing the algebra. How many times is the swap instruction ran? Well, it's a maximum of n times. Well, n minus 1 times, because you never have to swap the last element with itself. In our selection sort algorithm, the swap command runs once for every repetition of the outer loop, which runs n minus 1 times. So we could describe the cost of the algorithm as n squared minus n divided by 2 comparisons, or as n minus 1 swaps. Computer science uses information like the number of swaps and comparisons that the algorithm uses to predict how long it will take to run. These predictions rely on 2 important assumptions. Computers work by doing one thing at a time. Every single primitive operation takes a predictable amount of time in a particular implementation on a particular computer. That predictable amount of time is called the cost of the operation. These costs can differ based on the computer and the implementation. One computer might be able to compare 100 times faster than it can swap, and while another computer might be 100 times faster at swapping. We assign costs in time to these operations and calculate how long it would take a selection sort to run for arrays of different lengths. So if our time per swap is high, one computer takes 0. So the swap, because it's doing O of n, is not as important as the comparisons. For most sorting algorithms, the cost is described in terms of the number of comparisons between array elements. As you saw in this example, the cost in terms of swaps is misleadingly low for selection sort compared to the cost in comparisons, n squared minus n divided by 2. The number of comparisons will never be misleadingly low because any well-designed sorting algorithm will only swap elements after comparing elements. Without a comparison first, there's no way for an algorithm to know if a swap is even useful. Yay! I got my streak extended. Let's see what place I am on the leaderboard. Hopefully I haven't fallen behind. How do I find out my leaderboard position? Oh, hey, I'm number 1. Okay, we can skip doing any more brilliant. Alright, I'm almost done drinking my matcha here. In the morning I take this like steam shower, and I think that knocks out my energy a little bit. Okay, let's go. To this point in our study of systems, we have relied on a simple model of computer systems as a CPU that executes instructions and a memory system that holds instructions and data for the CPU. In our simple model, the memory system is a linear array of bytes, and the CPU can access each memory location in a consistent amount of time. While this is an effective model up to a point, it does not reflect the way that modern systems really work. In practice, the memory system is a hierarchy of storage devices with different capacities, costs, and access times. CPU registers hold the most frequently used data. Small, fast cache memories nearby the CPU act as the staging areas for the subset of data instructions stored in a relatively slow main memory. The main memory stages data stored on large, slow disks, which in turn often serve as staging areas for data stored on disks or tapes of other machines connected by networks. Memory hierarchies work because well-written programs tend to access the storage of any particular level more frequently. Boom, 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 boom. Sorry, I was just thinking about a problem that I was working on a couple weeks ago. Let me drink some more matcha here. Memory hierarchies work because well-written programs tend to access the storage at a particular level more frequently than they access storage at the next lower level. So the storage at the next level can be slower and thus larger and cheaper per bit. The overall effect is a large pool of memory that costs as much as the cheap storage near the bottom of the hierarchy, but that serves data to programs at the rate of the fast storage near the top of the hierarchy. As a programmer, you need to understand the memory hierarchy because it has a big impact on the performance of your applications. If the data your program needs are stored in a CPU register, then they can be accessed in 0 cycles during the execution of the instruction. So let me read that. If the data your program needs is stored in a CPU register, they can be accessed in 0 cycles during the execution of the instruction. If stored in a cache, 75 cycles. If stored in main memory, hundreds of cycles. And if stored on disk, tens of millions of cycles. What? Here then is a fundamental and enduring idea in computer systems. If you understand how the system moves data up and down the memory hierarchy, then you can write your application programs so that their data items are stored higher in the hierarchy where the CPU can access them more quickly, known as locality. Programs with good locality tend to access the same set of data items over and over again, or they tend to access sets of nearby data items. Programs with good locality tend to access more data items from the upper levels of the memory hierarchy than programs with poor locality, and thus run faster. For example, or on our Core i7 system, the running times of different matrix multiplication kernels that perform the same number of arithmetic operations but have different degrees of locality can vary by a factor of almost 40. In this chapter, we will look at the basic storage technologies, SRAM memory, DRAM memory, ROM memory, and rotating and solid-state disks, and describe how they are organized into hierarchies. In particular, we focus on the cache memories that act as staging areas between the CPU and main memory. Because they have the most impact on application program performance, we show you how to analyze your C programs for locality, and we introduce techniques for improving the locality of programs. You also learn an interesting way to characterize the performance of the memory hierarchy on a particular machine as a memory mountain that shows read access times as a function of locality. Next. Storage technologies. Much of the success of computer technology stems from the tremendous progress in storage technologies. Earlier computers had a few kilobytes of random access memory. The earliest IBM PCs didn't even have a hard disk. Really? I didn't know that. Was it just a tape drive or a floppy type thing? That changed with the introduction of the IBM PC XT in 1982 with its 10 megabyte disk. Let's ask AI. Oh, does OpenAI have an outage? Let's go here. Oh. Cassette tape. Yeah, exactly. That's right. Boom, boom, boom. All right. With its 10 megabyte disk, by the year 2015, typical machines had 300,000 times as much disk storage, and the amount of storage was increasing by a factor of 2 every couple of years. Random access memory, RAM, comes in 2 varieties, static and dynamic. Static SRAM is faster and significantly more expensive than dynamic RAM, DRAM. SRAM is used for cache memories, both on and off the CPU chip. DRAM is used for the main memory plus the frame buffer of a graphics system. Typically, the desktop system will have no more than a few tens of megabytes of SRAM, but hundreds or thousands of megabytes of DRAM. Static RAM. SRAM stores each bit in a bistable memory cell. Static RAM stores each bit in a bistable memory cell. Each cell is implemented with a 6-transistor circuit. This circuit has a property that it can stay indefinitely in either of 2 different voltage configurations or states. Any other state will be unstable. Starting from there, the circuit will move quickly towards one of the stable states. Such a memory cell is analogous to the inverted pendulum illustrated in figure 6.1. Pendulum is stable when it is tilted either all the way to the left or all the way to the right. From any other position, the pendulum will fall to one side or the other. In principle, a pendulum could also remain balanced in a vertical position indefinitely, but in this state is metastable. The smallest disturbance would make it start to fall, and once it fell, it would never return to the vertical position. Due to its bistable nature, an SRAM memory cell will retain its value indefinitely as long as it's kept powered, even when a disturbance such as electrical noise perturbs the voltages. The circuit will return to a stable value when the disturbance is removed. Inverted pendulum, like the SRAM cell, the pendulum has only 2 stable configurations for states. Characteristics of DRAM and SRAM. So we have transistors per bit. So SRAM has more transistors per bit. Access time, SRAM is way faster. Persistent, I don't know what they mean by persistent because it requires being powered on. I guess what they mean is it doesn't have to be refreshed, whereas DRAM I think has to be refreshed. Sensitive, I don't know what that means. SRAM is 1,000 times more costly with only 1/10 the access time. There's for cache memories. DRAM's used for main memory and frame buffers, graphics cards. Dynamic RAM. DRAM stores each bit as charge on a capacitor. This capacitor is very small, typically around 30 femtofarads. That is 30 times 10 to the negative 15 farads. What is a farad? Capacitance. Oh, they're saying small in its capacitance? I thought they meant small as in size, which would be nanometers or whatever. Anyways, femtofarads. Where did I leave off here? Recall, however, that a farad is a very large unit of measure. DRAM storage can be made very dense. Each cell consists of a capacitor and a single access transistor. Unlike SRAM, however, a DRAM memory cell is very sensitive to any disturbance. When the capacitor voltage is disturbed, it will never recover. Exposure to light rays will cause the capacitor voltage to change. In fact, the sensors in digital cameras and camcorders are essentially arrays of DRAM cells. Really? Various sources of leakage current cause a DRAM cell to lose its charge within a time period of around 10 to 100 milliseconds. Fortunately for computers operating with clock cycles times measured in nanoseconds, this retention time is quite long. The memory system must periodically refresh every bit of memory by reading it out and then rewriting it. Some systems use error-correcting codes where the computer words are encoded using a few more bits, such that circuitry can detect and correct any single erroneous bit within a word. Figure 6.2 summarizes the characteristics of SRAM and DRAM memory. SRAM is persistent as long as power is applied. Unlike DRAM, no refresh is necessary. SRAM can be accessed faster than DRAM. SRAM is not sensitive to disturbances such as light and electrical noise. The trade-off is that SRAM cells use more transistors than DRAM cells and thus have lower densities and are more expensive and consume more power. Conventional cell DRAMs. The cells bits in a DRAM chip are partitioned into D supercells. Each consisting of W DRAM cells. I feel like my brain is just still booting up. I think my neurons are more like DRAM than SRAM. In that I periodically have to refresh them. My synapses, the memories and information that I have encoded in my neural network, my biological neural network, requires refreshing periodically. What does the S stand for in SRAM? What does the S stand for in SRAM? Static. What about SD-RAM? SD-RAM is synchronous DRAM. Nature is by default asynchronous. And we impose this model of synchronicity onto circuits using clocks. And that terminology of synchronous and asynchronous circuits has been extended into software, where people use it to discuss things like invocating methods. So is this method a synchronous method where I will call it, I will wait, and I'll get a return value? And asynchronous, where I will start the invocation, I will go do something else, and at some point in the future I will wait for the value if I need to wait, and receive the value of the result of the subroutine. And also in networks, I think networks really show how asynchronous the world normally is. Synchronicity is hard to maintain and depends entirely on your locality. The further you're away from a component, the harder it is to maintain synchronicity in it. And there's a concept of synchronizing, which is like synchronizing data just means like copying data and keep it in sync between two locations, or synchronizing a clock. Like, let's synchronize our watches. It's like another concept of synchronization. But with relativity, there is no real true concept of synchronizing, because it depends on the relative velocities of the clocks. And if you and I synchronize our clocks, and then you go travel close to the speed of light, or go into a gravitational well, like, our clocks will have ticked off the same amount of time, but you will have drifted from me because of the relativistic effects of your velocity. Would it be velocity or acceleration? I think it's velocity. Yeah, it's your velocity. So when we meet again, our clocks could be totally out of sync. So because of general relativity, we lose the concept of instantaneous, or what's the concept? I forget the name of the word. But basically, like, there is no concept of like something that happens right now for two parties. You can have that instantaneous, not instantaneous, what's the word? Simultaneity. There is no simultaneous events. That concept just goes completely out of the window with relativity. Because you could be simultaneous in one frame of reference, as they say here, but then in another frame of reference, those two events were not simultaneous. One happened before the other. So in computing systems, we generally think of things as happening synchronously with a concept of simultaneity because of the clock. But once we get into larger computer systems that are distributed, we can't rely on concepts of simultaneity. Kind of curious. With relativity, can you have one frame of reference that observes event A happening before event B? Sorry, stop. Before event B, and another frame of reference that observes event B happening before event A. If so, would this impact causality? When the order can flip in special relativity, whether all observers agree on the order of two events depends on their separation in space-time. Space-like separated events, order can flip. If two events are too far apart in space for light or anything to travel between them in time, they are space-like separated. Different frame of reference can disagree. This is direct consequence. I'm talking about things that are less distant than so far apart that light or anything can travel. Time-like separated events, order cannot flip. If one event could causally influence the other, i.e. a signal at or below the light speed could connect them, they are time-like separated. All observers agree on the order. If A causes B, everyone sees A before B. Why causality is safe? Causality is protected by the structure of space-time. The light cone defines what can influence what, and no information can travel faster than light. So, if A and B can influence each other, order is fixed. If order can flip, they cannot influence each other. That's why no paradox arises. You cannot use a space-like ordering flip to send signals or create contradictions. So that means that for space-like time-like events, and most events that we would consider in our human experiences. Order is always preserved because these events are causally linked and can influence each other. However, we still do away with the concept of universal simultaneity, where in one frame of reference, event A and B happen at the same time, and in another frame of reference, event A happens before event B, then there can never be a frame of reference where event B happens before event A. What the hell's going on over there? It's not time to study relativity. Alright. Let's continue reading. I forget where we left off. I should really start keeping track of that. Alright, well, I'll just start at DRAM then. DRAM stores each bit as charge on a capacitor. Okay, the farads. Various sources of leakage current cause a DRAM cell to lose its charge within a time period of yeah, we read that. Figure 6.2 summarizes the characteristics of SRAM DRAM memory. SRAM is persistent as long as power is applied. Unlike DRAM, no refresh is necessary. Okay, we already read that. Conventional DRAMs. The cells in DRAM chips are partitioned into D supercells. This is where we left off. Each consisting of W DRAM cells. So D times W DRAM stores a total of D times W bits of information. The supercells are organized as a rectangular array with rows and columns where R times C is equal to D. Each supercell has an address of the form of ij, where I denotes the row and j denotes the column. For example, figure 6.3. shows the organization of 16 times 8 DRAM chip with D 16 supercells, W 8 bits per supercell. R is equal to 4 rows and C is equal to 4 columns. The shaded box denotes the supercell at address 2.1. Information flows in and out of the chip via external connectors called pins. Each pin carries a 1-bit signal. Figure 6.3 shows 2 of these sets of pins, 8 data pins that can transfer 1 byte. Oops. Aside, a note of terminology. The storage community has never settled on a standard name for a DRAM array element. Computer architects tend to refer to it as a cell, overloading the term with a DRAM storage cell. Circuit designers tend to refer to it as a word, overloading the term of word of main memory. To avoid confusion, we have adopted the unambiguous term supercell. High-level view of a 128-bit 16 by 8 DRAM chip. So you got a memory controller, you got a DRAM chip. We say we want row 2, 1. Okay. Figure 60 shows 2 of these cells, 2 of these sets of pins, 8 data pins that can transfer 1 byte in or out of the chip, and 2 adder pins that carry 2-bit row and column supercell addresses. Other pins that carry control information are not shown. Each DRAM chip is connected to some circuitry known as the memory controller that can transfer W bits at a time and to and from each DRAM chip. To read the contents of supercell IJ, the memory controller sends the row address I to the DRAM, followed by the column address J. The DRAM responds by sending the contents of supercell IJ back to the controller. The row address I is called a RAS, row access strobe request. The column address J is called a CAS, column, not a compared swap, but a column access strobe request. Notice that the RAS and CAS requests share the same DRAM address pins. I don't notice that. Okay, for example, to read supercell 2.1 from 16 by 8 DRAM in figure 6.3. That's a 4x4, not a 16 by 8. But yeah, in figure 6.3, the memory controller sends row address 2 as shown in figure 6.4a. The DRAM responds by copying the entire contents of the row buffer. Next, the memory controller sends column address 1 as shown in figure 6.4b. The DRAM responds by copying the 8 bits in supercell 2.1 from the row buffer and send them to the memory controller. One reason circuit designers organize DRAMs into 2-dimensional arrays instead of a linear array is to reduce the number of address pins on the chip. For example, if our example 120-bit DRAM were organized as a linear array of 16 supercells with address 0 to 15, then the chip would need 4 address pins instead of 2. The disadvantage of the 2-dimensional array organization is that addresses must be sent in 2 distinct steps, which increases the access time. So lower pins increase access time. No free lunch. Memory modules. DRAM chips are packaged in memory modules that plug into expansion slots on the main system board. Motherboard Core i7 uses a 240-pin dual inline memory module, DIMM, which transfers data to and from the memory controller in 16-bit chunks. Figure 6.5 shows the basic idea of a memory module. The example module stores a total of 64 megabytes using 8 64 megabit DRAM chips, numbered from 0 to 7. Each supercell stores 1 byte of main memory. In each 64-bit word at byte address A, main memory is represented by 8 supercells. Those corresponding supercell addresses is IJ. In an example, figure 6.5, DRAM 0 stores the first low order byte, DRAM 1 stores the next byte, and so on. To retrieve the word at memory address A, the memory controller converts A to a supercell address IJ and sends it to the memory module, which then broadcasts I and J to each DRAM. In response, each DRAM outputs the 8-bit contents of its IJ supercell. Circuitry in the module collects these outputs and forms them into 64-bit word, which it returns in the memory controller to the memory controller. Main memory can be arranged by connecting multiple memory modules to the memory controller. In this case, when the controller receives an address A controller selects the module K that contains A, converts A to its IJ form, and sends IJ to module K. Okay, we got a practice problem. The following: let R be a number of rows DRAM array, C the number of columns, B the number of bits needed to address the rows, and B, C the number of bits needed to address the columns. For each of the following DRAMs, determine the power of 2 array dimensions that minimize max and maximize the number of bits needed to address the rows or columns of the array. I don't think I need to get into this level of detail about DRAM. But that is conventional DRAMs. Now we have enhanced DRAMs. Non-volatile memory, which is going to be our ROMs. And then we get into disks. Enhanced DRAMs. There are many kinds of DRAM memories, and new kinds appear on the market with regularity as manufacturers attempt to keep up with the rapidly increasing processor speeds. Each is based on the conventional DRAM cell, with optimization that improves speed with which the basic DRAM cells can be accessed. Fast page mode DRAM, FPM DRAM. I've never heard of this one. A conventional DRAM copies an entire row of supercells into its internal row buffer, uses one, and then discards the rest. FPM or fast page mode DRAM, improves on this by allowing consecutive access to the same row to be served directly from the row buffer. For example, to read 4 supercells from row I of a conventional DRAM, the memory controller must send 4 RASCAS requests even though the row access I is identical in each case. To read supercell for the same row of an FPM DRAM, the memory controller sends an initial RASCAS request followed by 3 CAS requests. The initial RASCAS request copies row I into the row buffer and returns a supercell address by the CAS. The next 3 supercells are served directly from the row buffer and thus are returned more quickly than initial supercell. So that makes a lot of sense to me. When you're, again, with a spatial locality, if you're accessing memory around the area that you're currently accessing, that makes a lot of sense. I wonder if like all DRAM does that now, because I would wonder why you wouldn't want to do that. Extended data out RAM, EDO RAM, enhanced form of FPM DRAM that allows the individual CAS signals to be space coded together. Okay, so there's EDO DRAM, and then we got synchronous DRAM, which is what I am most familiar with. Conventional FPM and EDO DRAMs are asynchronous in the sense that they communicate with the memory controller using a set of explicit control signals. SDRAM replaces many of these control signals with the rising edges of the same external clock signal that drives the memory controller. Without going into detail, the next net effect is that an SDRAM can output the contents of its supercells at a faster rate than its asynchronous counterpart. Double data rate SDRAM. I've heard of this one, DDR SDRAM. I think we're on like DDR7 or something crazy. Explain the different types of memory commonly used in modern computing main memory. SDRAM, DDRs, etc. DDR5 is the current one. Okay. Low power DDR. Okay. Graphics DDR. High bandwidth memory. I've heard of these. These are used in GPUs. Yeah. AI accelerators. Yep. Okay. So we got a double data rate synchronous DRAM. Is an enhancement of SDRAM that doubles the speed of DRAM by using both clock edges as control signals. Different types of DDR SRAM are characterized by the size of a small prefetch buffer that increases the effective bandwidth. DDR2 bits, DDR2 has 4 bits, DDR3 has 8 bits. Video RAM, VRAM, used in the frame buffers for graphic systems. VRAM is similar in spirit to FPM RAM, DRAM. Two major differences are that VRAM output is produced by shifting the entire contents of the internal buffer in sequence, and two, VRAM allows concurrent reads and writes to the memory. Thus, the system can be painting the screen with the pixels in the frame buffer reads while concurrently writing new values for the next update writes. Interesting. Wasn't familiar with that. Okay, I'm going to take a quick bio break and then we'll continue reading about NVMe memory. Okay, sorry about that. I had a message a friend who works in memory about some of the stuff I'm learning about here. Yeah, EC memory. I wonder how many bits are dedicated for ECC. One bit per hour per gigabyte of memory. This is a really nice article here. Okay. Okay, let's continue reading. Non-volatile memory. DRAM and SRAMs are volatile in the sense that they lose their information if the supply voltage is turned off. Non-volatile memories, on the other hand, retain information even when they are powered off. There are a variety of non-volatile memories. For historical reasons, they are referred collectively as read-only memories, even though some types of ROMs can be written to as well as read. ROMs are distinguished by the number of times they can be reprogrammed, written to, and by the mechanism for reprogramming them. Historical popularity of DRAM technologies. Until 1995, most PCs were built with FPM DRAMs. From 1996 to 1999, EDO DRAMs dominated the market, while FPM DRAMs all but disappeared. SDRAMs first appeared in 1995 in high-end systems, and by 2002, most PCs were built with SDRAMs and DDR SDRAMs. By 2010, most server and desktop systems are built with DDR3 SDRAMs. In fact, Core i7 supports only DDR3 SDRAM. A programmable ROM, a PROM, can be programmed exactly once. PROMs include a sort of fuse with each memory cell that can be blown once by zapping it with a high current. An erasable programmable ROM, an EPROM, has a transparent quartz window that performs light to reach the storage cells. The EPROM cells are cleared to zeros by shining ultraviolet light through the window. Programming an EPROM is done by using a special device to write ones into the EPROM. An EPROM can be erased and reprogrammed on the order of 1,000 times. Electrically erasable PROM, an EEPROM, is akin to an EPROM, but it does not require a physically separate programming device, and thus can be reprogrammed in place on printed circuit cards. An EEPROM can be reprogrammed on the order of 10 to the power of 5 times. So that would be 100,000 times before it wears out. Flash memory is a type of non-volatile memory based on EEPROMs that has become an important storage technology. Flash memories are everywhere, providing fast and durable non-volatile storage for a slew of electronic devices, including digital cameras, cell phones, and music players, as well as laptops, desktops, and server computer systems. In section 613, we'll look at detail in the new form of flash-based disk drive known as a solid-state disk that provides faster, sturdier, and less power-hungry alternatives to conventional rotating disks. Programs stored in ROM devices are often referred to as firmware. When a computer system is powered up, it runs firmware stored in ROM. Some systems provide a small set of primitive input and output functions in firmware. For example, a PC's BIOS, basic input output system routines, complicated devices such as graphics cards and disk drive controllers also rely on firmware to translate I/O input-output requests from the CPU. Accessing main memory. Data flows back and forth between the processor and the DRAM main memory over shared electrical conduits called buses. Each transfer of data between the CPU and memory is accomplished with a series of steps called a bus transaction. A read transaction transfers data from the main memory to a CPU. A write transaction transfers the CPU to the main memory. A bus is a collection of parallel wires that carry address, data, and control signals. Depending on the particular bus design, data and address signals can share the same set of wires or can use different sets. Also, more than two devices can share the same bus. The control wires carry signals that synchronize the transaction and identify what kind of transaction is currently being performed. For example, in this transaction of interest to the main memory, for example, is this transaction of interest to the main memory or to some other I/O device, such as a disk controller? Is the transaction a read or a write? Is the information on the bus an address or a data item? Figure 6.6 shows the configuration of an example computer system. The main components are the CPU chip, a chipset that will call an I/O bridge, which includes the memory controller, and the DRAM memory module that makes up main memory. These components are connected by a pair of buses, a system bus that connects the CPU to the I/O bridge and a memory bus that connects the I/O bridge to main memory. The I/O bridge translates electrical signals of the system bus to electrical signals of the memory bus. As we will see, the I/O bridge also connects the system bus and memory bus to an I/O bus that is shared by our devices such as disk and graphic cards. For now, though, we will focus on the memory bus. So example bus structure that connects the CPU to main memory. So we have a CPU chip, we have register file ALU, and a bus interface that uses the system bus to talk to the I/O bridge, then talks over the memory bus to the main memory, or to other I/O devices connected to the I/O bus. A note on bus designs. Bus design is a complex and rapidly changing aspects of computer systems. Different vendors develop different bus architectures as a way to differentiate their products. For example, some Intel systems use chipsets known as the North Bridge and South Bridge to connect the CPU to memory and I/O devices. Respectively, the older Pentium and Core 2 systems, a front-side bus, FSB, connects CPU to the North Bridge. Systems from AMD replaced the front-side bus with a Hyper Transport Interconnect, while newer Intel Core i7 systems use the QuickPath Interconnect. The details of these different bus architectures are beyond the scope of this text. Instead, we will use a high-level bus architecture from Figure 6.6 as a running example throughout. It is simple but useful abstraction that allows us to be concrete, and it captures the main ideas without being tied too closely to the detail of any proprietary designs. Consider what happens when the CPU performs a load operation such as move A into REX, where the contents of address A are loaded into register REX. Circuitry on the CPU chip called the bus interface initiates a read transaction on the bus. The read transaction consists of 3 steps. First, the CPU places the address A on the system bus. The I/O bridge passes the signal along the memory bus. Next, the main memory senses the address signal on the memory bus, reads the address from the memory bus, fetches the data from the DRAM, and writes the data to the memory bus. The I/O bridge translates the memory bus signal into a system bus signal and passes it along to the system bus. Finally, the CPU senses the data on the system bus, reads the data from the bus, and copies the data into register REX. Conversely, when the CPU performs a store operation such as move REX into A, where the contents of register REX, I always do that. Boom, boom, boom. Where the contents of register REX are written to address A, the CPU initiates a write transaction. Again, there are 3 basic steps. First, the CPU places the address on the system bus. The memory reads the address from the memory bus and waits for the data to arrive. Next, the CPU copies the data from REX into the system bus. Finally, the main memory reads the data from the memory bus and stores the bits in DRAM. So you got a memory read transaction for a load operation. Okay. Disk storage. Disks are workhorse storage devices that hold enormous amounts of data on the order of hundreds to thousands of gigabytes, as opposed to the hundreds or thousands of gigabytes in a RAM-based memory. However, it takes on the order of milliseconds to read information from disk, and 100,000 times longer than from DRAM, and 1,000,000 times longer than from SRAM. They're slow as shit. This is a write transaction for store operation. Pretty similar. Disk geometry. Disks are constructed from platters. Each platter consists of 2 sides or surfaces that are coated with magnetic recording material. The rotating spindle in the center of the platter spins the platter at a fixed rotational rate, typically between 5,400 and 15,000 revolutions per minute RPMs. A disk will typically contain 1 or more of these platters encased in a sealed container. Figure 6.9a shows the geometry of a typical disk surface. Each surface consists of a collection of concentric rings called tracks. Each track is partitioned into a collection of sectors. Each sector contains an equal number of data bits, typically 512 bytes, encoded in the magnetic material on the sector. Sectors are separated by gaps, where no data bits are stored. Gaps are formatting bits that identify sectors. Boop. How? I'm not even going to go to the table of contents because fuck that. We're at 627. Let's assess these. Right, disk geometry. There we go. A disk consists of one or more platters stacked on top of each other and encased in a sealed package known as shown in Figure 6.9b. Okay, if we look at that disk geometry, we got our spindle, our platters, our surfaces, our tracks, gaps, and sectors, and then we got our platter view. The entire assembly is often referred to as a disk drive, although we will usually refer to it as simply a disk. We will sometimes refer to disks as rotating disks to distinguish them from flash-based solid-state disk SSDs, which have no moving parts. Disk manufacturers describe the geometry of multiple platter drives in terms of cylinders, where a cylinder is a collection of tracks on all the surfaces that are equidistant from the center of the spindle. For example, if a drive has 3 platters and 6 surfaces and the tracks on each surface are numbered consistently, then cylinder K is a collection of the 6 instances of track K. Disk capacity. The maximum number of bits that can be recorded by a disk is known as its maximum capacity, or simply capacity. Disk capacity is determined by the following technology factors: recording density, track density, and areal density. Recording density, the number of bits that can be sequenced into a 1-inch segment of a track. Track density, the number of tracks that can be squeezed into a 1-inch segment of the radius extended by the center of the platter. And areal density, which is bits per inch squared, the product of the recording density and the track density. Disk manufacturers work tirelessly to increase areal density and thus capacity, and this is doubling every couple of years. The original disk, designed in an age of low areal density, partitioned every track into the same number of sectors, which was determined by the number of sectors that could be recorded on the innermost track. To maintain a fixed number of sectors per track, the sectors were spaced farther apart on the outer tracks. This was a reasonable approach when areal densities were relatively low. However, as areal densities increased, the gaps between sectors where no data bits were stored became unacceptably large. Thus, modern high-capacity disks use a technique known as multiple zone recording, where the set of cylinders is partitioned into disjoint subsets known as recording zones. Each zone consists of a contiguous collection of cylinders. Each track in each cylinder in a zone has the same number of sectors, which is determined by the number of sectors that can be packed into the innermost track of the zone. How much is a gigabyte? Unfortunately, the meaning of prefixes such as kilo, mega, giga, tera depend on the context. For measures that relate to the capacity of DRAM's SRAM, typically K is 2 to the power of 10. For measures related to capacity of I/O devices such as disks and networks, typically K is 10 to the power of X. Rates and throughputs usually use these prefix values as well. Fortunately, for the back of the envelope estimate that we typically rely on, either assumption works fine in practice. For example, a relative difference between 2 to 30 and 10 to the 9 is not that large. Yeah, okay. And then there's also the Gibby bytes prefixes for powers of 2. The capacity of a disk is given by the following formula: the number of bytes per second, the average sectors per track, tracks per surface, surfaces per platter, platter per disk, which will give you bytes per disk. For example, suppose we have a disk with 5 platters, 512 bytes per sector, 20,000 tracks per surface, and an average of 300 sectors per track. Then the capacity of the disk is so and so. Notice the manufacturers express this capacity in units of gigabytes or terabytes, where 1 gigabyte is so and so. Practice problem: what is the capacity of disk? I don't give a shit. Disk operations: disks read and write bits stored on magnetic surface using a read-write head connected to the end of an actuator arm, as shown in Figure 610A. This is disk dynamics. The disk surface spins fixed rate rotational rate to the right and clockwise motion. The read-write head is attached to the end of the arm and flies over the disk surface on a thin cushion of air. By moving rapidly, the arm can position the read-write head over any track. So we got the read-write heads and the arms, multiple platter view. Okay. Disk operation. Disk read and write bits stored in a magnetic surface using read-write head connected to the end of the actuator arm. By moving the arm back and forth along a radial axis, the drive can position the head over any track of the surface in mechanical motion is known as a seek. Once the head is positioned over the desired track, then each bit on the track passes underneath. The head can either sense the value of the bit or alter the value of the bit. Discs with multiple platters have separate read-write heads for each surface, as shown in Figure 610. Heads are lined up vertically and move in unison. At any point in time, all heads are positioned on the same cylinder. The read-write head at the end of the arm flies literally on a thin cushion of air over the disc surface at a height of about 1 microns and a speed of about 80 kilometers per hour. Jesus Christ. This is analogous to placing a skyscraper on its side and flying it around the world at a height of 2.5 centimeters, 1 inch above the ground. With each orbit of the Earth taking only 8 seconds. At these tolerances, any tiny piece of dust on the surface is like a huge boulder. If the head were to strike one of these boulders, the head would cease flying and crash into the surface, also called head crash, a so-called head crash. For this reason, discs are always sealed in airtight packages. Discs read and write data in sector-sized blocks. The access time for a sector has 3 main components: seek time, rotational latency, and transfer time. Seek time, to read contents of some target sector, the arm first positions the head over the track that contains the target sector. The time required to move the arm is called the seek time. The seek time, t-seek, depends on the previous position of the head and the speed of the arm moves across the surface. The average seek time in modern devices, average seek, measured by taking the mean of several thousand seeks of 2 random sectors, is typically on the order of 3 to 9 milliseconds. I was going to say 3 milliseconds. Maximum time for a single seek, max seek, can be as high as 20 milliseconds. And that's like the main rate limiter for disk speed, or disk latency, I should say. Rotational latency. Once a head is in a position over a track, the drive waits for the first bit of the target sector to pass under the head. The performance of this step depends on both the position of the surface and when the head arrives at the target track and at the rotational speed of the disk. In the worst case, the head just misses the target sector and waits for the disk to make a full rotation. Thus, the maximum rotational latency in seconds is given by so-and-so. The average rotational latency is simply half of T max rotation. Transfer time. When the first bit of the target sector is under the head, the drive can begin to read or write the contents of the sector. The transfer time for one sector depends on the rotational speed and the number of sectors per track. Thus, we can roughly estimate the average transfer time for one sector in seconds as 1 RPM times average 1 over the average number of sectors per track times 60 seconds per minute. Okay, we can estimate the average time to access content of this sector as the sum of the average speed. Okay, I don't really care about these calculations because disks are so fucking legacy at this point. This example illustrates some important points. The time to access the 512 bytes in a disk sector is dominated by the seek time and the rotational latency. Accessing the first byte of the sector takes a long time, but the remaining bytes are essentially free. Yeah, exactly. Since seek time and rotational latency are roughly the same, twice the seek time is a simple and reasonable rule for estimating disk access time. The access time for a 64-bit word stored in SRAM is roughly 4 nanoseconds and 60 nanoseconds for DRAM. Thus, the time to read a 512-byte sector block from memory is roughly 256 nanoseconds for SRAM and 4,000 nanoseconds for DRAM, which would be 4 milliseconds. No, 4 microseconds, sorry. Decisentai milli micro nano. So yeah, microseconds, 4 microseconds. The disk access time, roughly 10 milliseconds, is about 40,000 times greater than SRAM, and about 2,500 times greater than DRAM. Don't care about that. Logical Disk blocks, as we see in modern disks, have complex geometries with multiple surfaces and different recording zones on the surface. To hide this complexity from the operating system, modern disks present a simpler view of the geometry as a sequence of B sector-sized logical blocks numbered from 0 to B-1. A small hardware firmware device in the disk package called the disk controller maintains the mapping between logical block numbers and actual physical disk sectors. When the operating system wants to perform an I/O operation such as reading a disk sector into main memory, it sends a command to the disk controller asking it to read a particular logical block number. Firmware on the controller performs a fast table lookup and translates the logical block number into a series of surface track sector. What was that? Where to leave off? Translates logical block number into a surface track sector triple that uniquely identifies the corresponding physical sector. Hardware on the controller interprets a triple to move the head to appropriate cylinder, waits for the sector to pass under the head, gathers up the bits sensed by the head into a small memory buffer on the controller, and copies them into main memory. Don't care about the practice problems on this one. We're just reading through. Format disk capacity. Before disk can be used to store data, it must be formatted by the disk controller. This involves filling in the gaps between sectors with information that identifies the sectors. Wait a minute. Let's reread that. Before disk can be used to store data, it must be formatted by the disk controller. This involves filling in the gaps between sectors with information that identifies the sectors, identifying any cylinders with surface defects and taking them out of action, and setting aside a set of cylinders in each zone as spares that can be called into action if one or more cylinders in the zones goes bad during the lifetime of the disk. The formatted capacity quoted by disk manufacturers is less than the maximum capacity because of the existence of these spare cylinders. Connecting I/O devices. Input-output devices such as graphics cards, monitors, mice, keyboard, and disks are connected to the CPU and main memory through an I/O bus. Unlike the system bus and memory buses, which are CPU-specific, I/O buses are designed to be independent of the underlying CPU. Figure 611 shows a representative I/O bus structure that connects the CPU, main memory, and I/O devices. Although the I/O bus is slower than the system and memory buses, it can accommodate a wide variety of third-party I/O devices. For example, the bus in Figure 611 has three different types of devices attached to it. A universal serial bus USB controller is a conduit for devices attached to a USB bus, which is a widely popular standard for connecting a variety of peripheral I/O devices, including keyboards, mice, modems, digital cameras, game controllers, printers, external drives, and solid-state disks. USB 3.0 buses have a maximum bandwidth of 625 megabytes per second. USB 3.1 buses have a maximum bandwidth of 1,250 megabytes per second. Boop. So now we're expanding into the I/O bus, where we have all of our fancy third-party devices. Graphics cards or adapters contain hardware and software logic that is responsible for painting the pixels on the display monitor on behalf of the GPU. A host bus adapter that connects one or more disks to the I/O bus using a communications protocol defined by a particular host bus interface. The two most popular such interfaces for disks are SCSI, pronounced SCUZZY, and SATA, pronounced SATA. SCSI, SCSI disks are typically faster and more expensive than SATA drives. A SCSI host bus adapter, often called a SCSI controller, can support multiple disk drives as opposed to SATA adapters, which can only support one drive. Additional devices such as network adapters can be attached to the I/O bus by plugging an adapter to empty expansion slots on the motherboard that provide a direct electrical connection to the bus. Accessing disks. While a detailed description of how I/O devices work and how they are programmed is outside of our scope here, we can give you a general idea. For example, Figure 612 summarizes steps that take place when a CPU reads from a disk. Boop. Advances in I/O bus design. The I/O bus in Figure 611 is simple abstraction that allows us to be concrete without being tied too closely with the details of any specific system. It is based on a peripheral component interconnect PCI bus, which is popular until around 2010. In the PCI model, each device in the system shares the bus, and only one device at the time can access these wires. In modern systems, the shared PCI bus has been replaced by a PCI Express bus, which is a set of high-speed serial point-to-point links connected by switches akin to the switched Ethernets that you'll learn about in Chapter 11. A PCI bus with a maximum throughput of 16 gigabytes per second is an order of magnitude faster than a PCI bus, which has a maximum throughput of 533 megabytes per second. Except for measured I/O performance, the differences between the different bus designs are not visible to application programs, so we will use a simple shared bus abstraction throughout the text. CPU issues commands to the I/O devices using a technique called memory mapped I/O. Interesting. Because the memory mapped I/O is a kernel thing, right? Using mmap. Oops, sorry, wrong one. Okay, didn't know that. Hardware aspects. Memory mapped I/O works by mapping device registers into a processor's address space. Device registers into process address space. Oh, okay. The device itself exposes certain physical addresses that, when accessed, are routed to the hardware device instead of regular RAM. For example, a GPU network card or disk controller respond to read writes to certain physical addresses by performing I/O operations. The CPU sees the address as normal memory, but the hardware interprets them differently. OS kernel aspects. The operating system uses a virtual memory system to make memory mapped I/O accessible safely in user space. On Linux, for example, the kernel provides functions like I/O remap to map device physical addresses into the kernel's virtual address space. User space programs then use mmap on a device file like devmem or a specific device driver to get access to these addresses in their virtual memory space. So the kernel provides the mechanism to map hardware memory map I/O into a process's virtual address space, but the existence of memory mapped I/O itself comes from the hardware design. The kernel is just a bridge. Summary: memory mapped I/O is hardware feature. Devices expose registers at specific physical addresses. Access from software managed by the OS kernel using mapping mechanisms such as I/O remap in kernel space or mmap in user space. Think of it like this: memory mapped I/O is a door built into hardware, and the kernel decides who gets a key and how they can use it. If you want, I can also explain how a memory mapped I/O differs from port mapped I/O and why some CPUs prefer one over the other. It's subtle but important for low-level programming. Do you want me to? No. All right. CPU commands to I/O devices use a technique called memory mapped I/O, which is in figure 612A, which is the next page. In a system with memory mapped I/O, a block of addresses in the address space is reserved for communicating with I/O devices. Each of these addresses is known as an I/O port. Each device is associated with or mapped to one or more ports when it is attached to a bus. As a simple example, suppose that a disk controller is mapped to port 0xA0, then the CPU might initiate a disk read by executing 3 store instructions to address 0xA0. The first of these instructions sends a command word that tells the disk to initiate a read, along with other parameters such as whether to interpret the CPU or whether to interrupt the CPU when the read is finished. We will discuss interrupts in section 8.1. The second instruction indicates a logical block number that should be read. A third instruction indicates a main memory address where the contents of the disk sector should be stored. After it issues the request, the CPU will typically do other work while the disk is performing the read. Recall that a 1 GHz processor with a 1 nanosecond clock cycle can potentially execute 16 million instructions in the 16 milliseconds it takes to read the disk. Simply waiting and doing nothing while the transfer is taking place would be enormously wasteful. After the disk controller receives the read command from the CPU, it translates a logical block number to a sector address, reads the contents of the sector, and transfers the contents directly to main memory without any intervention from the CPU. This process whereby a device performs a read or write bus transaction on its own without any involvement of the CPU is known as a direct memory access, or a DMA. The transfer of the data is known as a DMA transfer. After the DMA transfer is complete, the contents of the disk sector are safely stored in main memory. The disk controller notifies the CPU by sending an interrupt signal to the CPU. The basic idea is that the interrupt signals an extra pin on the CPU chip. This causes the CPU to stop what it's doing stop what it's currently working on and jump into an operating system routine. The routine records the fact that the I/O is finished and then returns control to the point where the CPU was interrupted. Okay, so one thing I wanted to ask AI here is when the kernel is idling with nothing to do, is the CPU actually running instructions like NOPs in a big loop, or is there some capability in the CPU that actually turns it off for a period of time where no instructions are executed? And if so, what is that capability called? When a kernel's idling, CPU doesn't just spin executing NOPs in a big loop anymore. Modern CPUs have mechanisms to stop or slow down execution to save power. Here's how it works. To just traditional busy wait idle, in very old systems, an idle loop might literally be a while true or a NOP jump loop. In that case, CPU executes instructions continuously, wasting energy, but modern kernels avoid this. The halt instruction. Most modern CPUs have an instruction called halt. When the CPU executes halt, it stops executing instructions until the next interrupt arrives, a timer, an I/O, or whatever. The CPU consumes less power. The kernel's idle task usually executes something like, while true, CPU idle. Eventually calls halt. CPU idle abstracts architecture-specific idle instructions. So when a CPU is truly idle, it can stop from executing instructions entirely, waiting for an event to wake up. Advanced CPU power states, C states. Beyond halt, modern CPUs support C states, which are sleep states. C0. Oops, dropped my pen. C0 is running normally. C1 is halt. CPU stops execution but can wake up quickly. And C2 through C3, etc. are deeper sleeps. Clocks are potentially or fully stopped, longer wake-up latency. Those can instruct the CPU to enter deeper C states during idle periods. Higher C states have more power but take longer to wake up. Save more power but take longer to wake up. On Linux, you can see them via the sys devices, system CPU, CPU 0, CPU idle, state star name. Let's try it. Cat sys devices system CPU 0, CPU idle state. Okay, I got 0 name, 1, 2, 3. Is there a 4 here? There's no 4. CPU idle. CD in there. And then we go under, let's do LT here. So you got the name, above, below, default status, description, disable latency, name, power, rejected residency, time, usage. Well, that's fascinating. No modern CPUs don't just access knobs and busy loops. The kernel executes architecture's specific idle instructions like halt, which stop instruction execution until an interrupt occurs. Modern CPUs have C states for deeper power saving modes when the CPU can't partially or fully turn off clocks. If you want, I can draw a diagram showing how the CPU is. No, I don't want you to. I hate that. Oops. Jump over to CSAPP, get status. Let's do a readme here. And we can start recording our progress on this chapter. So we are on what subsection here? Storage technologies. Yeah, we're still on the first one. Okay. Okay, we're gonna look at this diagram here. So this just shows the flow of data and control and interrupts. Okay, characteristics of a commercial disk drive. Disk manufacturers publish a lot of useful high-level technical information on their websites. For example, the Seagate website contains the following information and much more about one of their popular drives, the Barracuda 7400. Solid-state disk SSD. A solid-state disk SSD is a storage technology based on flash memory that in some situations is an attractive alternative to the conventional rotating disk. Figure 613 shows the basic idea. An SD package plugs into a standard disk slot on the I/O bus, typically USB or SATA, and behaves like any other disk, processing requests from the CPU to read and write logical disk blocks. An SD package consists of one or more flash memory chips, which replace the mechanical drive in the conventional rotating disk, and a flash translation layer, which is a hardware firmware device that plays the same role as a disk controller, translating requests from logical blocks into accesses to the underlying physical device. Figure 614 shows the performing characteristics of typical SSD. Notice that reading from SSD is faster than writing. The difference between random reading and writing performance is caused by the fundamental property of the underlying flash memory. As shown in figure 613, a flash memory consists of a sequence of B blocks, where each block consists of P pages. Typically, pages are 512 bytes to 4 kilobytes in size, and a block consists of 32 to 128 pages. Total block size ranging from 16 kilobytes to 512 kilobytes. Data are read and written to units of pages. A page can, let me ask AI here. Is an SSD page the same as a page in an operating system? Not exactly. The term page used in both contexts, but it means different things depending on whether you're talking about SSD or operating system. SD page. An SSD page is the smallest kind of unit in program that can be programmed written to NAND flash memory. So these are 4K to 16K depending on SD. Pages are grouped into blocks. While you can't write data to a page, you cannot erase a single page. Erase happens at a block level. Okay. So blocks are the main thing. OS page is the smallest unit of virtual memory managed by the operating system, typically size of 4K. Though in some systems supports 2 megabytes or 1 gigabyte huge pages, OS pages are used for mapping virtual memory to physical memory and for swapping to disk paging. Pages exist conceptually in RAM or as part of a page file on disk. They're about memory management, not hardware constraints. Boop. So yeah, that's one question I had, is that whether the pages in SSDs are the same as the pages in virtual memory. Data are read and written in units of pages. A page can be written only after the entire block to which it belongs has been erased. Typically, this means that all the bits in a block are set to 1 However, once a block is erased, each page in a block can be written once with no further erasing. A block wears out after roughly 100,000 repeated writes. Once a block wears out, it can no longer be used. Random writes are slower for two reasons. First, erasing a block takes a relatively long time, an order of 1 millisecond, which is more than an order of magnitude longer than it takes to access a page. Second, if a write operation attempts to modify a page P that contains existing data, i.e. not all ones, then any page in the same block with the useful data must be copied to a new erase block before the write to page P can occur. Manufacturers have developed sophisticated logic in the flash translation layer that attempts to amortize the high cost of erasing blocks and to minimize the number of internal copies on writes. But it's unlikely that random writing will ever perform as well as reading. SSDs have a number of advantages over rotating disks, but they are built of semiconductor memory with no moving parts and thus have a much faster random access time than rotating disks, using less power and are more rugged. However, there are some disadvantages. First, because flash blocks wear out after repeated writes, SSDs have potential wear out as well, where leveling logic in the flash translation layer attempts to maximize the lifetime of each block by spreading erasures evenly across all blocks. In practice, the wear leveling logic is so good that it takes many years for SSDs to wear out. See practice problem 6.5. Second, SSDs are about 30 times more expensive per byte than rotating disks, and thus typical storage capacities are significantly less than rotating disks. However, SSDs prices are decreasing rapidly as they become more popular, and the gap between the two is decreasing. SSDs have completely replaced rotating disks, and portable music devices are popular as disks replaces laptops and have been even begun to appear in desktop and servers. While rotating disks are here to stay, it's clear that SSDs are an important alternative. They weren't really here to stay. I have not seen a rotating disk in ages. Don't give a shit about the practice problems. Storage technology trends. There are several important concepts to take away from our discussion of storage technology. Different storage technologies have different prices and performance trade-offs. SRAM is somewhat faster than DRAM. DRAM is much faster than disk. On the other hand, fast storage is always more expensive than slower storage. SRAM costs more per byte than DRAM. DRAM costs more than disks. SSDs split the difference between DRAM and rotating disks. The price and performance properties of different storage technologies are changing at dramatically different rates. Figure 6.15 summarizes the price and performance properties of storage technology since 1985. Shortly after the first PCs were introduced, a number were culled from back issue of trade magazines and the web. Although they were collected in an informal survey, the numbers reveal some interesting trends. Since 1985, both the cost and performance of SRAM technology have improved at roughly the same rate. Access times and costs per megabyte have decreased by a factor of about 100. However, the trends in DRAM and disk are much more dramatic and divergent. While the cost per megabyte of DRAM has decreased by a factor of 44,000, more than 4 orders of magnitude, DRAM access times have increased by only a factor of 10. Disk technology has followed the same trend as DRAM and is even more dramatic fashion, while the cost of a megabyte of disk storage has plummeted by a factor of more than 3 million, more than 6 orders of magnitude. Since 1980, access times have improved much more slowly by only a factor of 25. These startling long-term trends highlight a basic truth of memory and disk technology is that it is much easier to increase density and therefore reduce costs than to decrease access time. DRAM and disk performance are lagging behind CPU performance. As we see in figure 615D, CPU cycles improved by a factor of 500 between 1985 and 2010. If you look at an effective cycle time, which we define as the cycle time of an individual CPU processor divided by the number of processor cores, then improvement between 1985 and 2010 is even greater. A factor of 2,000 is the split in the CPU performance curve around 2003 reflects the introduction of multi-core processors. See aside on page 614. After the split, cycle times of individual cores actually increased a bit before starting to decrease again, albeit at a slower rate than before. Note that while SRAM performance lags, it is roughly keeping up. However, the gap between DRAM and disk performance and CPU performance is actually widening. Until the advent of multi-core processors around 2003, this performance gap was a function of latency, with DRAM and disk access times decreasing more slowly than cycle time of an individual processor. However, with the introduction of multi-cores, this performance gap is increasingly a function of throughput, with multiple processor cores issuing requests to the DRAM and disks in parallel. The various trends are shown quite clearly in figure 6.16, with plots which plots the access and cycle times of figure 6.16, which plots the access and cycle times for figure 6.15 on a semi-log scale. What is a semi-log scale? I guess that means that it's linear on the x and log on the y. Let's ask AI. What is a semi-log scale? Okay, exactly. As we'll see in section 6.4, modern computers make heavy use of SRAM-based caches to try to bridge the processor memory gap. This approach works because of a fundamental property of application programs known as locality, which we'll discuss next. Locality. Well-written computer programs tend to exhibit good locality. That is, they tend to reference data items that are near other recently referenced data items, or that were recently referenced themselves. This tendency, known as the principle of locality. I'm gonna highlight that. Even though I obviously know a lot about locality, I feel like it's an important concept enough to highlight. Is an enduring concept that has enormous impact in the design and performance of hardware and software systems. Locality is typically described as having two distinct forms: temporal and spatial locality. In a program with good temporal locality, memory location that is referenced once is likely to be referenced again multiple times in the near future. In a program with good spatial locality, if memory location is referenced once, then the program is likely to reference a nearby memory location in the near future. Aside, when cycle time stood still, the advent of multi-core processors, the history of computers is marked by some singular events that cause profound changes in the industry and the world. Increasingly, these inflection points tend to occur about once per decade. The development of Fortran in the 1950s, the introduction of IBM 360 in the early 60s, the dawn of the internet called the ARPANET in the early 70s, the introduction of IBM PC in the early 80s, the creation of the World Wide Web in the early 90s. The most recent such event occurred early in the 21st century when computer manufacturers ran headlong into so-called power wall, discovering that they could no longer increase CPU clock frequencies as quickly because the chips would then consume too much power. The solution was to improve performance by replacing a single large processor with multiple smaller processor cores, each a complete processor capable of executing programs independently and in parallel with the other cores. This multi-core approach works in part because the power consumed by a processor is proportional to P is equal to FCV squared, where F is a clock frequency, C is a capacitance, V is the voltage. The capacitance is the total area of the core. Sorry, the capacitance, C, is roughly proportional to the area. So the power draw by multiple cores can be held constant as long as the total area of cores is constant. Okay, as long as feature size continue to shrink at an exponential Moore's law rate, the number of cores in each processor and thus its effective performance will continue to increase. From this point forward, computers will get faster not because clock frequencies increase, but because the number of cores in each processor increases, and because architectural innovations increase the efficiency of programs running on those cores. We can see this trend clearly in figure 6.16. CPU cycle time is reached. CPU cycle time has reached its lowest point in 2003. And then split off. And then actually started to rise before leveling off and starting to decline again at a slower rate than before. However, because of the advent of multi-core processors, dual-core in 2004 and quad-core in 2007, the effective cycle time continues to decrease at close to its previous rates. What time is it? We got about 30 minutes to 12. Okay, let's hop over to here. So we're gonna take our break at noon. Let's talk about locality. We got lots of reading on that, which is actually just a couple pages. Maybe we'll just finish locality and then take a break for lunch. So we have locality, memory hierarchy, cache memories. There's all stuff that was covered in the lecture, so I'm not like crazy about diving in deep here. Just want to get through reading the words into my brain, and maybe I'll pick up a few things here and there. Some more about caches, fully associated. Says he didn't go into detail in the lecture about the different types of caches, so that'll be good for me to have some background with. Issues with writes, anatomy of real cache hierarchy, performance impact of cache parameters, impact of cache sizes, impact of block size, impact of associativity, impact of write strategy. Writing cache-friendly code, that'll be helpful. And then we get into putting it together, the impact of caches on performance, program performance, the memory mountain. And that's the cover of the book, or the textbook, the hardcover. And that's it. Okay, so we're at 684, 641, and we started reading 616. So we made some pretty decent progress already. What was that, 24 pages? And we have ahead of us around 44 pages. So I think we can finish reading at least, not reading and doing the problems. I think we finished reading this chapter today, which will conclude all the memory hierarchy stuff. And then we move into, what is this? Part 2, running programs on a system and linking. We get into linking, which is really relevant to our learning Linux binary analysis stuff. To be honest, I'd rather learn about linking from this book than from the binary analysis book. Even though that one's shorter and more casual, I kind of do, like when I finish a section of this book, I kind of feel like I have a solid base of understanding. Whereas when I read that book over there, there's a lot of open questions still in my mind of like how things work. So, okay, what do I want to do? Do I want to finish? I think I'll take a break here. I'm getting kind of hungry. So I'm going to just say break here. This will be 11:30. And we're going to move lunch up to here. And we'll move our afternoon stream as well. And we'll see how I feel about dinner. But I will be back at 1 p.m. for the afternoon stream, where we will talk about locality and all the other fancy memory, cache memory, memory hierarchy stuff. Cool. All right, see ya.